In this chapter, we're going to talk about hardware description languages, or for short, HDLs. Hardware description languages allow us to describe logic, both combinational and sequential logic, using a language. And so we'll talk about how to describe combinational logic, how to describe delays, and that's only in simulation, sequential logic, combinational logic using what's called an always block, blocking and non-blocking assignments, finite state machines, parameterized modules, and test benches. So HDLs allow us to specify logic functions. It's a computer-aided design tool, or CAD tool, that will produce the synthesized gates from the description language that we use. Most commercial designs today are built using HDLs instead of schematics. Two leading HDLs are SystemVerilog and VHDL. SystemVerilog was developed in 1984 and was simply called Verilog, and became an IEEE standard, and it was extended in 2005 and is now called SystemVerilog. VHDL was developed in 1981 by the Department of Defense and is also an IEEE standard and was updated in 2008. So we first describe our circuit in the HDL of our choice. We're going to show how to do it in SystemVerilog. And then we can simulate our circuits. We can apply inputs and then check the outputs for correctness. And this simulation saves millions of dollars by debugging it before the circuit is put into hardware. And then we'll synthesize the circuit, which transforms HDL code into what's called a netlist, which describes the hardware, the gates, and the connections between the gates. So this is very, very important. This is why it's in red. Hardware description languages are not a programming language. So whenever you describe a circuit in an HDL, it's important to know what kind of hardware you expect to be synthesized from the HDL that you wrote. So if you think of it just as a software language, you'll get yourself into trouble because you'll produce hardware that either doesn't work or is so big that and unnecessarily big for what you need. So again, when you write your HDL, think of the hardware that you expect for it to produce. So there are two types of modules, behavioral module and a structural module. The modules have inputs. Here we show A, B, and C as inputs on the left and an output, Y, so they have an interface. But the difference between these two types of modules are that behavioral modules describe what the module does. So it describes the behavior of the circuit, but not how the components are put together. Structural modules, on the other hand, describe how the modules are put together. So they're built from submodules. And typically, the lower level modules are behavioral, and the higher level modules put those lower level behavioral modules together in a structural way, where we have a bunch of submodules that we instantiate and connect together. So here's an example module declaration in SystemVerilog. We can see here we have the name. In this case, we called it example. And this keyword module says, hey, the next thing that's going to happen is the module name. So we have module example. That tells us what the name of our module is. And now we have our inputs, in this case, A, B, and C. And we also have outputs. In this case, we have one output, output Y. So if we were to draw a black box of our system, this is what it would look like. And the other last thing that we need to have for our module declaration is this keyword end module that says, hey, that's the end of the module. And then we'll put some module body stating what the function of that module is. And we'll talk about that next. So here's a behavioral SystemVerilog module. And so we have our interface and the module keyword and name example, the end module keyword, and now we look at the body of the module. So what the function of the module is. So in this case, it's a sum of products. So y equals tilde a means not a. This ampersand sign means and then we have a not b, that tilde b, and not c. And this vertical sign means or, a, and not b, and not c. Another or, a, and b bar, and c. And so we've used SystemVerilog, this language, to describe what the behavior of this circuit is. We haven't said, hey, instantiate an AND gate and an OR gate. We actually let the synthesis tool decide, well, how do you want to implement this in gates? And so after we've written our SystemVerilog module, we can simulate it, and we can see A, B, and C. Here are inputs, and then we have our output Y, and we can see, well, let's see, A, B, and C are 0, 0, 0 to start, and we see that, in fact, we get A1 here because of this term, not A and not B and not C. We expect our output Y to be 1. When our inputs are 0, 0, 1, we expect our output to be 0 because none of these terms would force a 1 in that case, none of those product terms. And so we can, continue onward. Again, time is in the x-axis, increasing to the right, and the values are here in the vertical direction, A, B, C, and the output Y. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0 on A, B, and C, 1, 0, 1, 1, 1, 0, and finally our last value of 1, 1, 1. And we can probe through simulation and see what our output Y is, and if it's not what we expect, we can go back and change our SystemVerilog to make it correct, to correct it. And then the next step is we synthesize the SystemVerilog module, and the tool, the synthesis tool, turns our module into gates. And so we can see that it turned it into Y equals, here's our B bar, C bar, or A and B bar. And this is case sensitive. SystemVerilog is case sensitive, so even better would be to put those in lowercase, so we kind of recognize that case sensitivity. Y equals B bar, C bar, or A and B bar. And here's the A and B bar. And so we look at what we wrote up here, this assign statement. We assigned the output Y some value, and we notice, hey, actually that's different than what we wrote, or is it? Right? The synthesis tool used combining and said, oh, hey, these terms I can combine into B bar, C bar, right? Reduced the terms, and then said, oh, and actually these two terms, these last two terms, I could combine into A, B bar. And so the synthesis tool won't always minimize the equation, but in this case it did. It was easy. And so we noticed that, hey, our circuit is a little bit different than what we described, but it's the function is the same, and it used a minimum number of gates to produce that function. some SystemVerilog syntax rules. SystemVerilog is case sensitive, and this is where a lot of people get into some errors that they can't figure out. So for example, the signal reset with a lowercase r is different from the signal reset with an uppercase r. And so be careful with that. Those are two different signals because SystemVerilog is case sensitive. No names can start with number. So for example, 2mux would be an invalid name because it starts with a number 2. Mux2 would be valid, but not 2mux. White space is ignored, and we can write comments, and should in our SystemVerilog. A single line comment has 2 slashes at the beginning of the line, and multi-line comment has a slash and a star to begin it, and a star slash to end that comment. Here we have an example of a structural SystemVerilog module. So this module, NAND3, is a structural SystemVerilog module. And we can see that, well, it still has this interface, A, B, C, and Y. So if we drew a picture of a black box, A, B, C inputs, and the output Y. And now we notice, well, two things. First, there's this signal called N1. So logic indicates that it's just a signal, and it's an internal signal called N1. And we instantiate, inside of this module, we instantiate an AND gate. So this 3-input AND gate, AND3, and connect its output. So we can see the order A, B, and C happen to be the same names here. And the output is connected to this internal node. So the fourth interface signal, Y, is connected to N1. So we have A, B, and C. Here's our AND3 module that we've instantiated. And now we connect the output to N1, an internal signal. And then we instantiate a second module, this inverter module, INV. And this is the name of the module, and this is the instance name. So inverter is the instance name. We'd have inverter 1, inverter 2, inverter 3, right? This has to be the same as the module name, but then the instance name can be, our choosing. Can't start with a number though. So then we have our inverter, and we instantiate that and connect the input to N1. So again, the same order. This input is N1, and then the output we connect to Y. This is our inverter module. So this module is structural because we've instantiated these submodules, in this case, this AND3 module, 3-input AND gate, and the inverter, and connected them, internally inside inside this module, using this internal signal N1 that is not an input or output, it's just an internal signal.